2.3b. Let's talk about continuity algebraically. Okay. First of all, keep in mind a function is continuous on an interval if and only if it is continuous for every value of x on the interval. As a review, the continuity test has 3 parts. Number 1, for it to be continuous at c, the function has to have an f of c that exists. Part 2, the limit as x approaches c of f of x exists. And part 3, f of c equals the limit as x approaches c of f of x. So as a review from the last lesson, graphically, you could have something like this, where the point's up there. So in this case, f of c exists, that's fine. The limit exists because from either side it would be right there, but it's not continuous because f of c does not equal the limit as x approaches c of f of x. So that fails at step 3. Or you might have something like this, where f of c exists, but the limit as x approaches c of f of x does not exist because there's different limits on either side of that c. So that one would fail at step 2. So let's do some algebraic examples here using the continuity test. So let's say we have the function f of x equals x plus 4 when x is less than or equal to 2, negative x squared plus 8x minus 8 when 2 is less than x is less than 5, x plus 2 when x is greater than or equal to 5. So for the continuity test, essentially we're seeing, is this continuous everywhere? But we're going to check at 2 and at 5. So is the function continuous at 5? My question marks are weird, they look like 2, sorry about that. So first, does f of 5 exist? Yes, it's included and x is greater than or equal to 5, so f of 5 is 7. Step 2, the limit, and to find this we have to check both sides. So the limit as x approaches 5 from the left of f of x would be right here in the middle. That's just less than 5. So negative 5 squared, which is negative 25, plus 8 times 5. Negative 25 plus 40 is 15, minus 8 is 7. The limit as x approaches 5 from the right, that would be when x is greater than or equal to 5. 5 plus 2 is 7. Good. So those limits match. So then the limit as x approaches 5 of f of x equals 7. So the limit exists too. Step 3, well, f of 5 is equal to the limit as x approaches 5 of f of x, because they both equal 7. So yes, the function's continuous at 5. Now let's check if it's continuous at 2, because we have to check both places where the function changes direction, or basically all the numbers you see on the right over here with the inequalities. So step 1, f of 2, does it exist? Sure, x is less than or equal to 2, 2 plus 4. F of 2 is 6. Step 2, the limit as x approaches 2 from the left, that would be when x is less than or equal to 2 again, 2 plus 4, which is 6. Let's look at the right. The limit as x approaches 2 from the right of f of x is going to be here in the middle. So negative 2 squared, negative 4, plus 8 times 2, negative 4 plus 16 is 12, minus 8 is 4. Oops, those are not the same. So the limit as x approaches 2 of f of x does not exist. So it fails the continuity test. So no, the function's not continuous at x equals 2. So if the question is f of x continuous for all values? No, but it is continuous at 5. Here's another. F of x equals 5x plus 9 for x is less than negative 1, and x cubed plus 5 when x is greater than or equal to negative 1. And so our only spot we have to check is negative 1. So is x continuous at x equals, or not, is x continuous? Is the function f of x continuous at x equals negative 1? Well, let's see. 3 steps. Number 1, f of negative 1. Does it exist? Sure. For x is greater than or equal to negative 1, we have x cubed plus 5. Negative 1 cubed is negative 1, plus 5 is 4. Okay? It exists. Good. Number 2, the limit from the left. The limit as x approaches negative 1 from the left of f of x. That's going to be x is less than negative 1. 5 times negative 1, negative 5, plus 9 is 4. Good. From the right, the limit as x approaches negative 1 from the right of f of x. From the right, we have negative 1 cubed is negative 1 plus 5 is 4. So both limits on either side are the same. So the limit as x approaches negative 1 is 4. So we're good. Check. So step 3, well, yeah, f of negative 1 equals the limit as x approaches negative 1 of f of x equals 4. So we're good. So yes, the function is continuous at x equals negative 1. And so it's continuous everywhere for our purposes. Couple more. F of x equals 7x plus 2 for x is less than 1. Square root of x plus 24 for x is greater than 1. So we'll check if it's continuous at 1. So our first step, what's f of 1? Well, it doesn't exist, right? It's not included in either of these inequalities. So it fails the continuity test right away. Nope, not continuous at x equals 1. Let's look at f of x equals x squared minus 9 over x squared plus 8x plus 15 when x is less than negative 3. Cubed root of 9x for negative 3 is less than or equal to x is less than 0. And x squared over 9 for x is greater than or equal to 0. So we will check continuity at negative 3 and 0. Let's do negative 3 first. So continuous at x equals -3, question mark. That yes looks like a 2 with a dot underneath it, I've been told. So first, f of -3. f of -3 would be -3 squared, 9 minus 9, which is 0. The denominator would be -3 squared, 9 minus 24 plus 15, which is 0. So as far as a value, this does not exist. If we were finding the limit, sure, we can take out a whole and all that stuff, but when we get 0 out over 0, we know it's a removable discontinuity, and the value does not exist. You know what? I just did something totally wrong, and I'm sure you guys all caught me, but we're 10 minutes in, so I'm just going to erase and go back. Okay, so if you were thinking, but like, why did you plug it into that one? Exactly, I don't know. Okay, so at x equals -3, this middle function applies, because that's where the less than or equal sign is. So f of -3 would be the cubed root of -27, which is -3. So that's fine. The limit as x approaches -3 from the left of f of x would be 0 over 0. So we have to try again, right? So we're going to have to do the limit as x approaches -3 from the left of f of x is going to be the limit as x approaches -3 of x plus 3, x minus 3, over, this will factor into x plus 3 times x plus 5. So the x plus 3's will go away because there's our whole. If we plug -3 in here, we get -6 over 2, or -3. Now the limit as x approaches -3 from the right of f of x will be this middle one, so the cubed root of -27, which is -3. So those limits match, meaning they're the same. So the limit as x approaches -3 of this function is -3. Step 3, are these the same? Yeah, f of -3 is equal to the limit as x approaches -3 of f of x, which is equal to -3. So yes, the function is continuous at -3. Now we'll try 0. So continuous at x equals 0. Step 1, f of 0. Well, looking up here, that'll be included right here. X is greater than or equal to 0. 0 squared over 9 is just 0. That exists. Let's do the limit. So the limit as x approaches 0 from the left of f of x, from the left is less than 0 right next to it, so it'll be right here. The cubed root of 9 times 0, cubed root of 0, is just 0. The limit as x approaches 0 from the right will be when x is greater than or equal to 0. 0 squared over 9, 0 over 9 is just 0. So then the limit as x approaches 0 of f of x is 0. So the limit exists. Step 3, yeah, f of 0 equals the limit as x approaches 0 of f of x, which equals 0. So it's continuous. So since we checked at both places where the function changes definition, this function is then continuous everywhere, or for all real numbers.